This episode is brought to you by those red circles and arrows that seem to be all over YouTube lately. Hey, did you see that first Wonder Woman trailer? Yeah, I don't know if you noticed this toward the end, but there was a moment where Wonder Woman had a giant sword hidden in the back of her dress. Yeah, I don't know how I missed it either. It was only there literally in the middle of the screen. But thanks either way, IGN. Also, remember that little kid in Attack of the Clones? Well, I don't know if you knew this or not, but that was Boba Fett. I know, right? It all makes sense now. Honestly, who's the dummy that keeps doing this stuff? Oh. But anyway, intermolecular forces. Intermolecular forces are usually taught at the beginning of General 2. Sometimes people teach it at the end of 1, but I think most of the time it's 2. That's where I'm going to put this anyway on my playlists. But to understand how intermolecular forces work, all you really need to understand is how magnets work. And everybody knows how a magnet works. Well, almost everybody. But yeah, magnets have oppositely charged ends or poles, and opposite charges attract. So the first intermolecular force you usually learn are dipole-dipole forces, or dipole forces for short. And a dipole force is the main intermolecular force for most polar molecules. You take a molecule like hydrogen chloride. It's polar, and with the positive end being on the hydrogen side, the negative end being on the chlorine side. So if it comes near another polar molecule, like another hydrogen chloride, just like magnets, opposite charges attract. So the negative end of one molecule gets attracted to the positive end of another molecule, or vice versa. And you usually have a bunch of these types of molecules in a given place, so you get a bunch of these interactions going on. Now, there's another type of intermolecular force called hydrogen bonding, and that's really just a special type of dipole force. It pretty much works the same way as your regular dipole forces, but it's seen to be special. The thing that makes it special is that they seem to be significantly stronger than your run-of-the-mill dipole forces. And the way you spot hydrogen bonding, hydrogen has something to do with it, clearly, but not any old hydrogen. You're looking for a hydrogen bonded to a nitrogen, oxygen, or fluorine. Those types of hydrogens can be attracted to the N, O, or F of another molecule. And if you look, it's pretty much the same kind of interaction as the hydrogen chloride we saw a minute ago. Positive of one molecule attracted to the negative of another. But like I said, this interaction is seen to be significantly stronger than other types of molecules. So you take water, for example. Yeah, water is a polar molecule, negative at the oxygen end, positive at the hydrogen end. Just like with HCl, you can, opposite charges attract. So, negative end of one molecule will be attracted to the positive end of another water molecule, or whatever the molecule is. And as you go deeper into this chapter, you'll start talking about things about, how intermolecular forces affect different states of matter, or things like boiling points and melting points. And when you get into that stuff, you'll have a better understanding of why hydrogen bonding was given its own class. But finally, the nonpolar molecules, their main intermolecular force is dispersion forces. And a dispersion force, or London force as they're sometimes called, not after the city of London, some guy named London, or sometimes they're actually mashed together into London dispersion forces. But a dispersion force is essentially a temporary dipole. Polar molecules, they're polar all the time. But nonpolar molecules, they can become temporarily polar. And that's because, the electrons that are around those molecules, they're not static. Most of the time they're distributed symmetrically around a molecule. But those electrons are zipping around all the time, and you can have these, and there are cases where they can become polar. And there are two types of ways you can form these temporary dipoles. You have what we call instantaneous dipoles, and induced dipoles. And kind of like the name implies, an instantaneous dipole is one that happens instantaneously, all of a sudden. So if you can imagine a nonpolar molecule being a sphere, it doesn't have to be a sphere, but that's what we're doing. So again, the electrons are distributed symmetrically around that molecule. But as they're zipping around all over the place, they can temporarily become or briefly become lopsided. You have more electrons on one side or the other, and that gives you a brief dipole moment. But nonpolar molecules on average are symmetrical, so it'll eventually even out and go back to being nonpolar. But an induced dipole, like the name implies, it's a dipole that was induced, caused by something else, and that something else can be an ion, like a sodium ion, gets near a nonpolar substance, and again, opposite charges attract. The positive charge from that ion will pull electrons toward it, or if you have an anion, it'll push electrons away, causing that molecule to be temporarily polar. And if the two things move away from each other, then it'll go back to being symmetrical. Or you could have a polar molecule get near a nonpolar molecule, and that can cause a brief induced dipole. Or let's say you have two nonpolar molecules near each other. One of them suddenly becomes an instantaneous dipole. That's going to cause the other guy to become an induced dipole. So the instantaneous induces the other. So you can imagine a nonpolar substance, like in our last case. You have all these nonpolar molecules. You just have all these brief instances all of the time, all over the place, of instantaneous dipoles occurring, and they're inducing dipoles in other guys, and it's happening again all over the place, and enough to keep them attracted to one another, depending on what state of matter you're in. But again, that'll be a discussion for another time. A couple other things, though, we'll want to talk about with induced or with dispersion forces. First off, you hear this term called polarizability, how polarizable a molecule is. That just refers to how easy it is to distort that electron cloud. And in general, the bigger the electron cloud, the bigger the molecule, the easier it is for that cloud to get distorted. And if you kind of think about it, that kind of makes sense. The bigger that cloud, the more it's going to be able to sort of move or jiggle around. Also too, the burp made me cause memory loss, made me forget words. Anyway, what was I talking about? Oh yeah, polarizability. But I was done with that. I'm moving on. Also, another thing to keep in mind about dispersion forces is that we talk about them in context of nonpolar molecules. They are the main intermolecular force of nonpolar molecules. But these dispersion forces occur in all molecules, polar and nonpolar. For polar molecules, its main intermolecular force is going to be dipolar hydrogen bonding, but there are dispersion forces there as well. And one way to kind of make sense of that is that if you go back and think about a hydrogen chloride molecule, that polarity essentially came from that single bond, the electrons being pulled toward the chlorine end. But that's two electrons, and that molecule has more than two electrons. The rest are usually arranged symmetrically around that molecule. I mean, it's not a sphere, it's more toward the chlorine end, but they're symmetrical. And again, you can have these instantaneous dipoles occurring for those electrons. And like I said before with hydrogen bonding, we'll talk about other stuff later on, like boiling points and melting points, that lets you see how we can tell that those dispersion forces are there. All right. So that'll be it, and we'll talk about that other stuff some other time. But for now, bye.